So in this video, I am going to discuss the force response. This is the forcing function, and we have a RL circuit. So we want to see how the RL circuit behaves when there is a forcing function present. So let us write it as V naught ut, and we are trying to find the current through the inductor. And remember, we came up with this expression from the previous video that IT was equal to V naught over R minus V naught over R e raised power minus R over L T. So I want to do a little discussion here before I move forward. So this is known as the forced response. Response means output, and the output in this circuit that we were interested in was the current through the inductor. So this is the forced response. And look at this part. This part, we have V naught a constant, R is a constant, so this term is constant, it's not going away. So as time increases or time passes, this term is going to stay here. This is the steady state response. This is the steady state response, or this is the, in a way, we can say, this is a response that takes the form of the forcing function. So this is a response. This is a part of IT. So this part is the response that has a form equal to or matching. Sorry, not equal to, matching the forcing function. This is constant. This is constant, and this part is the is a decaying exponent, and we have seen such a term when we were solving for the natural response of RL circuit, where there was no voltage source and the inductor already had energy in it, and we saw how the energy was released in this circuit, how that circuit, this connection R and L in series, basically behave whenever they are connected in a circuit. So this the form of this is basically related to the natural response of the circuit. So this term is has the form of the natural response. It is not the natural response. It has a form like the natural response. This has form like the forcing function, and overall this is the force response of the circuit. So we will come to some discussions later on, but um let us try to uh, develop an intuitive understanding of this thing. So let us have another look. So can you see this does not depend on time? So for example, if I ask what will this term be after 10 seconds have passed, so it will still be the same, is a constant. But after 10 seconds have passed, this term is going to be a smaller value as compared to what it was at the start, that is at t is equal to 0. At t is equal to 0, this term would be, so by the way, we should have some prior knowledge of the circuit, and whenever we come up with the response or result, we must always compare it and see whether it matches with our understanding of the circuit or not. So we know that the initial current in this circuit, because there is inductor in there, is 0. We already know this thing. So if we put t is equal to 0 here, do we get that? So I0 or 0 plus is e raised power 0 is 1. So we get 0 here. So it matches this thing. But what happens when t is infinity or a large time has passed? So e raised power minus infinity is 0. So this term becomes 0. So you see, this term vanishes with time. It vanishes with time. Or if we say the same thing in another way, so we can say that when time, a large time or lot of time has passed, this term becomes 0. So what does this mean? This means that when a large time has passed, this is going to stay. This is the steady state response of a circuit. And what is this? This is not going to stay forever. It is going to stay for a small time. We will come to that later on. I hope you remember that we found the importance of this thing, five time constants, 5 tau. 5 tau is usually that time independent of the circuits, whatever the circuit there is. In 5 time constants for that circuit, a circuit, uh, a circuit moves from the transient state to the steady state. Steady state. So this term is known as the transient. Sorry, not tau is t. Transient state or transient response. Sometimes, most often, we don't use this word state here. So it is transient response. So you see, it makes sense. Transient is going to die out. It is transient in nature, but the steady state part is going to stay there. And if you look closely, how can we arrive at this steady state response by mere inspection of the circuit? Can we find this, or does our understanding of the circuit understand or help us find this term directly? So remember the discussion of the inductor. Now inductor is just a piece of wire. So for a piece of wire does some magic, basically, that is known as that self-induction, and we will come to the other thing later on. But that induction is a process through which a varying current is going to induce a voltage across its terminals. When the current is varying, a voltage gets induced here. But when the current, ultimately things settle down, current is not varying, there is a constant flow of current here later on, then there will be no current here, no voltage across this. So the voltage across this will be zero. What kind of thing this is, where the voltage across its terminals becomes zero, but the current is flowing, for example, between these two terminals. So there is current flowing, but there is no voltage across this. It's a short circuit. So inductor behaves as a short circuit after a long time has passed, or 5 time constants. So when 5 time constants have passed, or a long time has passed, an inductor behaves as a short circuit. What does this mean? The voltage across it becomes zero, not the current. The current will become constant. The current through the inductor becomes a constant value, and derivative of a constant is zero. That is why voltage is zero. We understand that. So what happens when the voltage here becomes zero? All this voltage V naught appears here. So what will be the current through the resistor when the voltage across it is V naught? The current will be V naught over R. And you see, it matches our understanding. So when a long time has passed, or the transient have died out, the inductor behaves as a short circuit, and all the current in the circuit will be based on this and this alone, and that is this thing. So just check this statement of and this inspection. We can just inspect the circuit and understand the steady state behaviors. This is the steady state behavior of the inductor in steady state. Let me write this thing as well. In steady state, or when 5 time constants have passed. So we assume that after 5 time constants, the element enters in the steady state. So it behaves as a short circuit. So what will happen? The voltage across it will be zero, and KVL states that this voltage then will appear here. So we can determine the current. So we know how to find the final current at t is equal to infinity. We know by infinity, many 5 time constants would have passed. So the circuit would definitely be in steady state. So we already know that in this circuit, I infinity will be V naught over R. So in a way, you can say that this term is the final current, or we can write it like this as well, IF. The final current would be V naught over R. or this is not the final value, sorry, this is the final one. This is the forced part, the the term of current that matches the forcing function. The forcing function is constant, so this is a constant as well. So that is, this F is for the term that matches the forcing function, or let us say the forced part of the response. This is not the complete force response, that this is that, but it is the part that matches the forcing function. And if we come to this thing, can you see that its nature or its form is a decaying exponent, and the circuit, whenever R and L are there, they have the response as a decaying exponent. Energy in the circuit settles in a decaying exponent form. So this is what we term as the natural response that we have already discussed. There is more discussion to this, and I am going to do this in the next video in detail again, because we want to understand this thing on this very basic simple circuit. Let us discuss everything on this circuit, and then when we will come to RC circuit, for example, we are going to use our learning of the discussion here, and we will apply that to there straight away. We are not going to solve that in a very long fashion. For example, in the previous video, we came up with this expression by solving an integral, a differential equation, and that was not easy. It involved understanding of calculus as well, and we are not very good at that. At least I am not very good at that. So we will not like to do that again and again for different circuits. So what we are going to do? We are going to see how the response looks like, and we are going to exploit our understanding. For example, a part of the response I have just explained to you can be found from the ultimate steady state behavior or the final value. So this part is the part that resembles the forcing function. Let us represent it like this. And this part resembles the natural response. So the overall response, the force response, is the overall response comprises of these two parts, and we have just seen that how to find this one. So we may come to that, the other one, later on, but I hope this discussion is helpful here. I would want to continue uh, uh, with some other discussion, but for now, just to keep the video short, I am ending this video. I will start the discussion again in the next video.